Right. So now, for current electricity, basically, let's first explore some of the symbols and their names. Now, these symbols are, for you, it's not that important, but in A2, you might use them. So it's good that you remember. So I'm gonna first, just draw the symbols and then write their names. So you guys can just also just draw the symbol and leave some space for the description, right? Just one or two lines. Hmm. Okay, these are the ones very useful. And this is a connecting lead. This is a cell. This is a battery. Resistor, fixed, and DC supply, and junction of wires. These are overlapping wires. This is a filament bulb. This is a voltmeter. This is an ammeter. This is switch open. This is switch closed. This is a variable resistor. This is a microphone, a loudspeaker, and fuse, and LDR. LDR stands for light emitting Light dependent resistor, my god. Then this is a thermistor. This is a diode, and that's basically LED, light emitting diode. Okay, please write this down. Right. Now you guys have written it. Should I go forward then?
Yes, sir.
Okay. Now current. So current is defined as the rate of flow of charge at a point in the circuit. Now the current is I, it's charge upon time. The SI units for current is ampere, which is A, and it is a scalar quantity, and it is measured by an ammeter. Okay, now so basically current has two different directions, and both directions are absolutely fine because they really don't interfere in any of our calculations. So I'll copy this. Okay, so current basically goes from positive to negative. That sort of current is called the conventional current, that goes from positive to negative, right? And the current basically in reality goes from negative to positive because electrons can only move, and it's called electron flow. It goes from negative to positive. Now the thing is that why do we have two types, and why does it not matter? Usually we want to take the first one as a convention, so we'll keep that. But the reality of this is that suppose there is a doctor's room, and then right outside that room there is a waiting area, okay, with 3 chairs only. So what happens is that suppose there is a person who's sitting in the line like this. And then if this person basically goes into the doctor's office, Suppose all of these are negative and consider the chairs being positive or vice versa. So when the person moves to the doctor's office, this seat becomes empty. So the next person basically comes here and sits on the chair, making this seat empty. And then this person comes here and sits here, making this chair empty. So you might realize that the negative charges are going this way, but the positives, like the chairs, the empty chairs are moving in this way. Although they're not moving relatively, like the last chair is emptying, the new person can come in. So basically, with our perspective, we can say both currents are correct. Do you guys understand this? Yeah. So it is just, a way of seeing things. So in any case, we'll follow conventional currents. So you have to do that. Now, in the exam paper, a lot of times they're going to ask you the definition of Coulomb, right? So you should write it that 1 Coulomb of charge is when it flows past a point in the circuit in a time of 1 second when current is 1 ampere. Check नहीं किया अभी. Now elementary charge. Now elementary charge is basically the smallest value of charge any particle can have. Like we can, well, it could be smaller. Charge could be, no, it cannot be, probably. Yeah, it could be smaller, but this is not the smallest value. That's the, in fact, let's correct this. This is the standard value of charge of an elementary particle, which is basically 1 electron is equal to 1 elementary charge is equal to 1.6 times 10 raised to minus 19 coulombs, and this is basically the value of charge on a proton or electron. So that's the value. You should remember this. Although this is given in the exam paper, that would be nice to remember this. Okay. Okay, now, so suppose in a question it says that current carrying a wire has 10 amperes of current that passes a point in 2 minutes. Now it says calculate number one, the charge passing, and number two, number of electrons passing. Okay, like that. So first of all, you say charge is equal to current into time. So the current was 10, time was 2 into 60. So that's total of 1200 coulombs. And they say number of electrons. So we'd say if one electron has 1.6 times 10 raised to minus 19 coulomb of charge, then n number of electrons will have 1200 coulombs, right? So you cross multiply. So it's going to be 1200 divided by 1.6 times 10 raised to minus 19, and that should be around 7.5 times 10 raised to power 21 electrons will make up this much charge. Is that clear? Aisha Namad?
Yes.
Sir, can you explain it again?
Yes, why not? Just give me a second then. Okay. Oh crap. Okay, Ahmad, you do understand how to calculate the charge, right?
Yes.
Okay. So what I'm saying is that it says how many electrons are passing, which means that if one electron has 1.6 times 10 raised to power minus 19 coulomb of charge, then n number of electrons will have 1200 coulomb of charge. Do you understand? It's just like that.
Yes.
So you cross multiply then. So it will be 1200 divided by 1.6 times 10 raised to power 19. So this will give you about 7.5 times 10 raised to 21 electrons that will have this much charge. Do you understand? They will make up this 1200 coulombs. Understood?
Yes.
Okay, you can write this down, please. Interesting. Okay. Now, then we're gonna go towards electromotive force, and this is electromotive force, which is generally called as EMF, and the potential difference. Now they may ask you both the definitions called as PD, so you need to learn both the definitions very, very clearly. So it will be a 2-mark definition, and for the first mark you will write work done per unit charge. So this is the first mark for both of them. Once you have written that, then basically the next mark is for work done per unit charge by the battery to move a charge round a complete circuit. Alright, so this is the second mark for this. When you write it, you get 2 marks. Now EMF itself, like you can see from the definition, it's work done per unit charge or energy per unit charge, which is the same thing. The SI units for EMF are joules per coulomb or volts, which is capital V, right? Now, potential difference, however, has a different path from this. It is work done per unit charge in dissipating. Dissipating means that you're converting electrical energy to other forms across any 2 points in the circuit. I'll show you how. So potential difference has the exact same formula, work done per unit charge or energy per unit charge, exact same units, joules per coulomb or volts, but a different concept altogether. Okay. Now I just want to tell you this very important fact about it, that these two are scalar and measured by voltmeter. Okay, you can write this down, please. Okay. Okay. Now, what you're going to do is you should understand that when you make a circuit, for example, there is a battery or a cell, right? And then basically there are 3 different resistors. I'm sure you guys have done it in IGCSE, so you already have the concept. So when you put a voltmeter across the battery, it basically shows you the EMF. So let's suppose it shows you like 120 volts, let's suppose, right? Now current is going, charges are taking 120 joules per charge, right? Like that. So when it reaches this point, so right now at this particular point we have 120 volts. It's just like, suppose you get a $20, $120, and then your father gives you, so your father becomes the EMF because he's providing you some money, right? Energy per unit charge. And then you try to spend it. So let's suppose you're like entering the first shop. So you have $120 in your pocket, right? Now, when you leave the shop, you buy something, and now you only have $100 left. What it means is that if I want to find the potential difference, the difference in voltage that has become, then the voltmeter here would show me 20 volts. It means around this particular component you have dissipated electrical energy equal to 20 joules per coulomb. Is that clear? Hamad and Aisha?
Sir, could you repeat?
So Aisha, before this point, suppose you had $120 that the battery has given to you, right? When you enter the shop, you exit it, now you have only 100 left. So how much did you spend? 20. So that is the potential difference. So when a charge goes, so this is the amount of voltage or energy per unit charge that is dissipated or converted across this component. Do you understand?
Yes, sir.
Now you enter the next shop, and then when you leave the shop, you only have about, say, 40 left, which means if I put a voltmeter across this component, what would be the potential difference here? The potential difference here would be 100 minus 40, 60 volts. Do you understand? And of course, the last one, when you leave out, basically you will have no volts left because you go back to the battery then. So the last one will here show you a potential difference of 40 volts. Do you understand, Hamad?
Yes.
Now, if I say that I want to connect a voltmeter from this point to this point, so what do you think the value would be here? Any idea? Now it would be 80 volts. Why? Because now it's actually giving you the potential difference of the first resistor and the second resistor together. Do you understand?
Yes.
So what you see is potential difference, which means that every point, this, and this, 0, right? These values that you see are basically called the potential. Potential means the current voltage they have. And then when you take a difference between 2 points, it becomes potential difference. And that's what the definition says. It says work done per unit charge in dissipating electrical energy in other forms across any 2 points in the circuit. Understood? If taking how much potential is lost or decreased. Done? All right. So I think that would be it then for today. And I will see you tomorrow. And then we talk about this more. Okay.